The talk today will be about ZKP security. I'm Gyumin Roh. My nickname is RKM0959. I'm currently head of security. Head of security researcher manager at an audit firm called KALOS. We have been recently exploring with the new hot topic of the blockchain world, which is ZKP. So we're doing some ZKP audits. We are currently good friends with Zelic and trying to cook up some ZKP auditing with them. So from my recent experiences, I have cooked up some surveys and got myself some opinions about how we should view the ZKP security world. So in this talk, I'll try to talk to you about how I think about how I view the ZKP security world and what we can learn from our previous audits and security-related lessons. Okay, so the story begins with my opinions on how the ZKP development cycle works. So basically, when you develop something, you will first have a rough idea about what exactly you are going to build. So you're going to start with some, at least quote-unquote, documentation about what your application will look like, how it will behave, what's the input and what's the output, and how the state will change, and stuff like that. So from there, you will change your written documentation into code, obviously. So to do that, you will figure out what exactly you need to check. So for example, I want to build this AMM or something like that, and to build such AMM, I need to check this, I need to check this, I need to check this. So if I check if A, B, C are true, then the AMM works correctly, so everybody's happy. So if you finish that kind of process, you will end up with a list of raw constraints to check. So from there, you will, since this is ZKP, you will spend some time trying to arithmetize that list of raw constraints into a ZKP circuit. So by implementing your ZKP circuit, you will take those raw constraints and turn it into a ZKP arithmetization. And alongside that, since you need to generate proofs and stuff like that, you will also have witness generating logic. So that is the third stage, so the ZKP arithmetization and the witness generation. And from there, you will apply whatever system you are trying to apply. For example, it could be just Planck over a BN254 curve. So you apply those cryptographical magic, and somehow, some way, we will end up with the final prover and the verifier logic. So there are 3 or 4 steps regarding the development cycle, depending on how you look at it. And the main point I'll be trying to make is that each of those 3 or 4 steps are, there might be some vulnerabilities that are attached to one of these steps. So for example, what kind of vulnerabilities could happen in the specification part of the development cycle? So for example, if you're developing an AMM, you might want to check that your specifications actually make sense. So for example, this is true in literally every software development cycle, I might imagine. If you're developing an AMM, regardless of whether you're just doing it raw in Solidity or doing it in a ZKP-like way, you might want to check that the AMM specifications make sense. So for example, if I'm a user and I swap 100 USDC for some Ethereum and then sell those Ethereum for USDC immediately afterwards, if I have more than 100 USDC, then something is obviously wrong. So you might want to perform a sanity check of your app design before you do anything, and that's the 0th part, the specifications. And now we get to the second part, the step 1, which is what you have to check. So just a reminder. So now that we are done with the specifications, now we move on to the list of raw constraints. So basically, here you end up with, to make this application, I need to check A, B, C, and D. And now there's now I'll show you this table. The top row shows whether a specific test case input matches the specs or does not matches the specs. And on the left side, we have whether the test case input passes the list of checks you described or fails the list of checks you described. So the obvious incorrect cases are The first one is the over-constraining, where the inputs does match the specifications, but fails the list of checks you described. In this case, it means that you got worried too much, and you added too much checks, and now the list of now that the things that should obviously work fails. So, for example, you're writing on ERC20, and apparently, like, I have 1,000 USDC, and I try to send some person 500 USDC. It obviously should work because I have more than 500 USDC, but somehow, some way, the ERC20 developers got too worried and added a bunch of unnecessary checks, and somehow I can't send my USDC. That's obviously a big issue. And while in ZKP security, usually the more emphasized mistake between the under constraints and over constraints is the under constraints, but because it happens much more, But at the same time, we should not take the over constraints very lightly. It's clear that, for example, if you're over constraining stuff, some stuff that actually should pass does not pass, then it could definitely lead to some issues like, for example, denial of service and other issues of that sort. And those are definitely not the type of vulnerabilities to take lightly. So one point I'm trying to make here is that over-constraining is, while it is not very intuitive, it is still a very important class to take note of. And the second one is relatively simple. It's the under-constrained one, where the inputs that does not match the specs actually pass the checks. So you need to add more checks into your list of checks to do. And this is also obviously very important. Like, for example, if there's under constraints in the ZKVM, then maybe you could like push 6 bytes even though the opcode is push 5 and something like that. So the point being, from the first 3, oh, and also another point I will try to make here, because we have a lot of time, is that while usually in ZKP security, when we're talking about under constraints, it usually discusses the mistakes in the arithmetization side, but sometimes under constraints can happen by just like forgetting a check. For example, like in Solidity security, in smart contract security, obviously there are like quote-unquote novel attack vectors like reentrancy and stuff like that, but at the same time, a good chunk of vulnerabilities come from just business mistakes. So like forgetting a check, like forgetting how the business logic should work and stuff like that. So here, for example, on the just simply forgetting a check thing, if your ZKP application deals with elliptic curves, as a lot of the applications do, like for example, if you're doing like BLS 12381 curves and BLS signing and stuff like that, you will definitely deal with elliptic curves while writing a ZKP circuit. And if you are dealing with those stuff, you might want to check if you're reviewed that your circuits deal point doubling correctly, because the formula is different from the case where you're adding 2 different points. Also, in that case, maybe your circuits are not dealing with the point at infinity incorrectly, and you might want to check that. And these two issues are like not ZKP. Does not come from the ZKP thing. It comes from the elliptic curve and how to deal with things. So. Point being, not all under constraints bugs are like truly, their essence does not come from the ZKP side. Their essence comes from like the actual application side. So point being, from the first 2 steps is that the security fundamentals are still very relevant. Even though like ZKP security is this really like unexplored, relatively unexplored, mysterious landscape, it's still security. So the stuff you learn from basic security principles still carry over to this new world of ZKP security. So for example, the resolution from this is basically you need to check whether your application design actually makes sense. And this is true in literally every software in the world, not just ZKP software. And these parts pretty much says that you need to make sure that your list of test case inputs are very good. Like it covers a lot of different parts and stuff like that. Its coverage is very good and stuff like that. And this is true in pretty much every single software development, not just ZKP. So yeah, the conclusion from the first two steps is that the security fundamentals from other areas are still very much relevant in the ZKP world. So now the main fun part of the ZKP world, ZKP security world, is the circuit implementation. The bulk of ZKP-specific vulnerabilities or mistakes come from this side, where you take the raw constraints and somehow, some way, arithmetize it to your choice of the ZKP. So this list comes from the ZK bug tracker repository on GitHub by Xerox Park and Kyle at Ethereum Foundation. And it lists some common vulnerability types. And these are really the main dish of the ZKP security. So I'll just read them out real quick. So under constrained circuits, non-deterministic circuits, overflows and underflows, bit length issues, unused public inputs that are optimized out, frozen heart vulnerability, trusted set of leaks, and the discrepancy between assignments and constraints. Okay, so from here, the idea that I had that I would like to share with you is this. So if you look at the list and take these 4 vulnerability classes, so overflows, underflows, range check issues, and bit length issues, and if you look at these vulnerability classes and think deeply why these vulnerability classes are possible, the conclusion that I had is that these issues, these vulnerability classes are possible because our proof system, for example, BN254 Plonk, deals the whole arithmetization thing over a 254-bit prime field. So since we are dealing everything over a prime field, and not something that we are used to dealing with, like the set of integers or something like that, because of this we deal with the prime field kind of thing, we have to be careful about overflows because prime field wraps around P. We have to be careful of range checks because obviously everything wraps around P. There's nothing such as negative integers in a prime field and stuff like that. So point is, from a vulnerability class, we can think about it and deduce what part of this arithmetization tactic leads to this kind of a vulnerability. So what we can do thinking in reverse, what we can do if we want to create new types of bug classes, new types of bugs, is that we can start from the nature of the arithmetization tactic, and then from there we think about how this part of the, for example, if we're dealing with Plonk, what part of Plonk could lead to a vulnerability? So let's think in this way and think about what kind of vulnerability classes that we can think about. So one part of Plonk that is very important and used prominently in ZKP circuits is the use of a lookup table. So lookup tables obviously used a lot these days to improve performance and stuff like that. And one issue that was recently found is the dynamic lookup table issues. So basically what happened is that the usage of dynamic lookups is very tricky, and sometimes the developer can make a mistake and it could lead to a soundness bug because of a quote-unquote evil row in the dynamic lookup table. So to briefly explain, usually the lookup table is fixed column, usually, but sometimes you actually need for performance to use a lookup with an advised column. And what could happen is that, for example, if there's 3 rows here, what could happen is that the first 2 rows are constrained properly, so they have no issues whatsoever. But the 3rd row is not constrained at all. So what we can do what a malicious prover can do to use this to their profit is to maliciously change this unconstrained third row and then use that malicious value to look up things. So the lookup argument is still verified, but since this third value is designed maliciously, they can do whatever they want and possibly even break the protocol. So that's what happened, and this kind of shows that if you think about lookups and think deeply about how lookups could break stuff, then we could see this bug class and think about think that this is derived from the nature of Plonk that we use, which is that we use lookup arguments. Okay, so and another thing that is used prominently in ZKP circuits is selectors. And there are various ways where selectors being used improperly could lead to a vulnerability. So one is the selector enabling logic being flawed. And the second is the misuse of selectors that aren't actually fixed columns. So we'll showcase the two with some examples. The first example is from the Scroll's Poseidon circuit. So we recently audited Scroll and found this interesting bug. So what happened is that this is from the Poseidon hash table, and what happens is that they begin with filling the first one or two custom rows, and it returns the offset to begin the main hash table body rows. So you see that filling the custom rows returns the offset, and then the offset is used as an argument for the hash table body function. And the number of custom rows, 1 or 2, is determined based on whether this Boolean value NPT only is true or not. And what happened was, in the case where NPT only is true, they return 1 as the offset. So in other words, the main hash table body rows is started at offset 1, but at the same time they enable this this selector called scustom. The scustom is basically a selector which denotes whether this row is a custom row or not. So they made a mistake of enabling this custom this selector at offset 1. So in reality, these two logics should have been swapped at their positions. And it also happens so that there was a gate created that if the scustom is turned on, i.e. it's a custom row, then the hash inputs and control value, the control value is the remaining amounts of bytes to be hashed, are forced to be equal to 0. So what happened in conclusion is that since the first row of the hash table body is mistakenly set as a custom row, the first inputs, the first hash inputs and the first control value is mistakenly over-constrained to be equal to 0. So this breaks the entire hash table, which is pretty bad. And another thing, the second part where we discussed this one. Yeah, the misuse of selectors that aren't actually fixed columns. So here, so sometimes we select the constraints based on expressions over a prime field or columns that aren't actually a fixed column. So for example, if we want to select a constraint based on some value being 0 or non-zero, then we could we could calculate the is0 chip and then take the is0 expression and then use it as a quote-unquote selector for a gate. And in some rare cases, selectors are actually just defined as advice columns. So you have to prove that it is constrained properly to act as a selector. So for example, this is the Poseidon hash circuit from the ZK EVM at PSC or Scroll. And you see that this S-sponge continue thing is obviously a selector. It's named like a selector, but it's a column advice. So it's an advice column, not a fixed column, but it still acts like a selector. So we actually spent some good amount of time proving that this S-sponge continue is properly constrained to act as a selector for this specific logic. And another point about selectors is that sometimes it doesn't really matter if the selector values are Boolean. For example, if I'm using a selector Q to denote that if Q is turned on, then this expression is forced to be 0, then usually the developers will write it in the form of Q times expression is equal to 0. In this case, all that is important to force that expression is equal to 0 is the fact that Q is non-zero. So Q doesn't have to be exactly 1 to force that the expression is 0. Q can be 5, Q can be 6, Q can be 7. It can be anything except 0 to force that this expression is 0. So in this case, even though Q is not Boolean, everything is fine. You just need to check that if Q is turned on, then Q is non-zero. That's the only important thing. However, this isn't the only case where selectors are used. One other case that is definitely possible is you are using a selector with a lookup argument. And this is the case that gets interesting. For example, if you are claiming that this Q times expression is inside a table T, let's just say fixed table, a fixed table T, there are two things that you need to be concerned about. The first thing is that since if Q is 0, this should be immediately true because the lookup arguments are turned off. It should be immediately true, and that means that 0 should be inside this table. And you need to check that 0 being inside this table doesn't break your protocol. You can mangle with the table to deal with this issue. The another thing is that if the lookup argument is turned on, you might want to check that this Q thing is actually 1. So for example, if Q times expression is inside T and Q is non-zero, that is not enough to force that this expression value is inside T. Because if Q is 2, for example, that means 2 times expression is inside the table, not expression. So you might want to check that this Q value is actually Boolean. You need to constrain it properly to make sure that your lookup argument isn't flawed. So for example, to quote-unquote prove that this is actually a possible attack vector, I'll show you a close call. This wasn't a full vulnerability, but this was a close call in the ZK EVM. So for example, in the bytecode circuit, the ZK EVM checks that this tuple of opcode and push size is valid by utilizing a lookup table. So basically, push 5 corresponds to 5, push 10 corresponds to 10, and so on. And for this lookup argument, the selector was an AND, a multiplication of 3 things. I'll show you with the code, but one is the fixed column of fixed selector of Q enable, a fixed column selector Q last, which should be turned off, and finally the tag of the row, which is expected to be 1 for byte and 0 for header. So here we have the code. So basically, the enable is an AND, a multiplication of these 3 things, and the third is byte thing is the tag, and this enable thing is used here, to force the lookup argument to actually happen when enable is turned on. And the problem here was that the issue was, not issue, but the main idea was that this tag value, which is derived from the is_byte meta part of the code, is actually an advice column. So it can be anything it wants. And at the same time, it was never actually directly constrained to be a Boolean value. So what we could do here is that since this is_byte thing is not necessarily Boolean, that means that the enable value is not necessarily Boolean either. So what we could actually do is, since push 5 is opcode 0x64, which is 100, and push 5 obviously pushes 5 bytes, this 100, 100,5 is actually inside the lookup table. And this means that we can actually put tag to equal 5, opcode to equal 20, and push size to equal 1. So since 5 times 20 is 100 and 5 times 1 is 5, this actually passes the lookup argument. But at the same time, it's very clear that 20, as in opcode, does not equal push 1. So this is actually a flaw. The opcode and push sizes are not matched correctly. But thankfully, there were some like other checks going around, so like this wasn't a full bug. But anyways, this was a pretty cool idea. And the conclusion being that with a ZKP backend and the arithmetization tactic, we can think about how certain properties of the tactic, for example, the usage of prime field, the usage of selectors, the usage of lookups, and so on, can lead to vulnerabilities. So this could be an interesting way to deep dive into certain bug classes, to divide the taxonomy of the bug classes. And certainly, the more bug classes we have, it will be more fruitful for developers, security researchers, auditors, and maybe even tooling builders. So this is one way to think about the taxonomy. And there's the final part, which is the cryptographical magic. And there are two subsections in this final cryptography section of the vulnerabilities. One is that the backend cryptographical magic part is just implemented incorrectly. And one is the developer is misusing the framework. For example, in the forward part, we could say that the trusted set of leak is on this side because it's not dealing with the toxic waste, quote unquote toxic waste properly. Or for example, if you're talking about frozen heart, it means that your backend is not dealing with Fiat-Shamir heuristic correctly, and so on. And a special case here is the optimized out public inputs. This is dealing with the gross 16, gross 16. And the reason that this is in between these two things is that this vulnerability class can be handled on the back end, but also can be handled on the developer side. So, for example, this optimized out public inputs thing can be handled on the back end. For example, Snark.js has some dummy constraints to stop this whole optimized out public inputs thing, and now the developers don't really have to worry about it anymore. But at the same time, the developers can just by themselves add these dummy constraints so that they don't have to worry about this issue anymore. So it's interesting. So this kind of bugs can be handled on the back end by the actual tooling developers, or it can be handled on the developer side who actually uses those toolings. So point being, the conclusion being that so since the optimized out public inputs thing is a very very not easy nature of gross 16, we should think more about like the new ZKP techniques in this security-focused way. So for example, recent few years in ZKP research have brought out very cool tactics and technology. For example, there's like snark aggregation, recursive snarks, there's starks, there's like a bunch of polynomial commitments, there are a bunch of new arithmetization tactics, and there's like folding schemes, there's like a lot of very cool developments going on, but at the same time, we haven't really started to pulling these into our development cycle. We haven't really thought that much about the secure usage of these tactics, these technologies. So my claim is that we might want to start the study on secure usage of these ZKP techniques, and it will be a very interesting topic. And the solution for these new discoveries on potential vulnerabilities might be in the backend / tooling side, but it might be also on the developer side, or maybe it's just both. So vulnerability classes that are similar to the relation between gross 16 and the public inputs being optimized out. This technology and vulnerability mapping should be an interesting topic for study in folding scheme and some type of vulnerability or something like that. So it'll be very cool to think about this, and that's the point. So we have covered all 4 steps of the ZKP development quote-unquote cycle, and discussed how each part can lead to a potential vulnerability class. So that's the talk, and I would like to thank Kyle for the ZK bug tracker and some nice discussions prior to making this presentation. Xerox Park and their security group, which has taught me a lot of things, and Scroll for allowing me to share some findings here and allowing me to, me and the friends at Zelic to audit their circuits. It's been an honor, and you can contact me at my personal email or my work email or whatever. So thank you.